welcome everyone for this little 101 session, introduction session to JuMP. We're going to have two notebooks today, one about JuMP and one more about disjunctive programming. I'm Stephan Sahm, organizing the Julia User Group Munich. And today, after quite some time, actually, again, an introductory session by myself. We had a lot of other speakers presenting online at Julia User Group Munich, and I'm also happy we had another on-site session last month. This also worked out nicely, so I'm happy to be back in 2024. Then let's start right into JuMP. You have the Jupyter notebook. I hope every one of you was able to click on the link in the README, which has these two notebooks linked, which directly go to a binder link. And actually, this might go off somewhere if you're not using it for some time, because they are, of course, saving resources. And because of this, there's a button at the top always with launch binder. In case it just breaks down, you can click exactly this link and it will restart the notebook itself. So that's pretty handy. We have some resources available. So mine has 4 GB of RAM, pretty good for a binder actually. So we shouldn't experience any problems on resources. And also everything is quite small. Okay, so I'm happy to go into it. We first, as a little summary. So this is really a relatively straightforward and hands-on introduction. So there are, of course, many details you can find on jump.dev, the documentation of it. And this is more, getting it relatively straightforward, simple with a couple of examples and a couple of kind of what I use myself when using JuMP. And so we start with a JuMP model, which will be our global state, so to say, which stores all the descriptions, all the constraints, all the variables. It's our global configuration object, and it's usually initialized often initialized with an optimizer. And here we use the Heis optimizer because I don't know better actually. So this is the usual optimizer, which is also used in the tutorials. But there are definitely probably also others. Gurobi, or how it's pronounced, is kind of the most, or it's often referenced, but it's a proprietary solver where you can get free academia license, I think. But there should also be other solvers which you can use. And of course, also JuMP is an ecosystem on its own, so different solvers can solve different things. But we'll look into the basics. So I'm trying to make everything as simple as possible to have the feeling that you can use JuMP to do stuff. So the first thing you'll realize is that JuMP is actually not directly related to programming, but it's really a language defined in Julia. So you can use Julia, you can use loops and all this kind of around it, but the key thing will still be kind of relying on a couple of primitives. And the first one is variable. So we can define a variable, and actually, like we will see later, we can also define several variables at once. And and there are essentially 3 kinds of variables. The standard one is a float variable, which is kind of defined by not specifying any type at all. And as you see here, this variable syntax has special support to also provide lower and upper bounds for our variables, which is often used in these kind of optimization problems which we're going to solve. And another way of writing is that we have then this third argument, which is the type. Here's a binary type. And there's another completely different style. It's the anonymous style. We can also mix this. But in case sometimes you may stumble upon it that you don't want to have a named variable, but really anonymous variable, which is helpful inside loops or the like. And then, it's sometimes, it is this way with keyword arguments. Looks not so nice maybe, but it works. And it's good to know that this exists and that you can use it. And yeah, and all, so let me execute this. I just realized that my first cell is actually still executing. So I'm probably in exactly this state that my backend dropped a while ago. So I'm going to click on Launch Binder again and going to open a new tab, which is going to run the background. I will switch to it as soon as it's there. So you are invited to execute all the cells, of course, also on your end. I'm using Shift Enter usually, which directly jumps then to the next cell, but you can also use this button here, the Run button. And yeah, and I'm happy. My new notebook is already there. I hope you have a similar smooth experience. So now again, running the first one. So these variable and actually also the constraints, which we're going to look into in a second, they are all stored on the model itself. And if they are named, you can actually access them using the index brackets by the name itself, but as a symbol, as is usual in Julia. So actually looking at everything, there's this object dictionary method in JuMP where you see all the references which are stored on the model. And this is also the kind of the first, a little bit advanced thing, that this is a typical thing how you work with JuMP. So in your function, you may define kind of all the variables just like named variables, but later in another function, you would like to access the same stuff, and then you can just have a little assignment like your variable one equals like this reference from your model, and then you can continue working on it. So this is quite nice. And yeah, because of this, it's sometimes necessary to use the anonymous style, because if they are named, there should be only ones. And if you like to kind of add stuff in the loop, then no way for naming this. Okay, let's look into the second part. And as always, of course, you're invited to ask questions. And I just overlooked one. So there's one question in the chat. The question is whether this binary type means Boolean, and it's not the exact. It's not kind of a Boolean itself, because it's, I think, a special type from JuMP itself. But I myself am thinking of it like that. So like Boolean in Julia can also be easily converted into integers. This binary is also like easily combined with integer values. And my gut feeling would say that it's kind of, even a bit tighter integrated into integers, that it might be that on some solvers it's actually implemented just as an integer. I'm not 100% sure about all these solver internals, but I can imagine that the relationship is even tighter. Thank you for the question. And and to admit, I'm not sure why it's usual to use the bin type and not the bool type. But I think it's because of some potential confusion, and hence they have their own type. If someone else from the crowd knows a better answer, feel invited to join the chat. Okay, so let's move on to constraints. Constraints are kind of the key part of what JuMP is about. You actually want to formulate, kind of whatever constraints you want. You have some function of some inputs, and then you have constraints, usually smaller equal or larger equal something. If you want strict comparisons, you have to model this yourself by using some epsilon. And now the different solvers can solve different kinds of constraints. And we are now just sticking to some linear part, some linear transformations, which are, in general, easier to solve because of convexity features. But there are also support for nonlinear parts and also something in between. So we have this conic optimization and another quadratic optimizations, which are in between the linear and the nonlinear parts, and yeah, can be solved by more solvers. In general, you can take a look at the solver overview of JuMP and see which kind of problems they can solve. You use standard Julia in here, and yeah, but you will be notified if something cannot be solved by the solver you're using. So again, there's a named and an anonymous constraint syntax. In this case, it's a bit more straightforward. The name is given as an extra argument separately from the constraint, because the constraint just refers to the given variables. But as before, these are also stored on the dictionary itself. Only the name ones, of course. And also with a nice representation. Okay, so the last part, and then you already can describe all your scheduling problems. Let me kind of give one step back. Actually, I just forgot to explain what kind of constraints we have here. So the first one is just multiplying our variable 1 by 6 and comparing it to 3 plus 100 times our binary variable. So in case the binary variable is 1, this constraint will be kind of a bit higher. And in case the binary variable v2 is 0, then then the second constraint will be active actually. And this kind of just a little introduction, because we're going to look at similar stuff later on in disjunctive programming. Okay, so next to the constraints, we have the objectives. And actually, this is optional. You can also kind of describe just your constraints and look for something feasible. But yeah, having an objective is usually then the better thing to go. And yeah, and we're just minimizing in this case. JuMP has support for multiple objectives. So you can take a look there. But yeah, classic is min or max of something. And then finally, solving our model is pretty straightforward. We just call optimize. We get some fancy output, which you're going to see how to suppress this in a second. And we see from the output that our solution was found and is actually optimal. And now an important check whether the model is actually solved or and feasibly solved. And if not, you should throw an error or some other return value which you recognize actually, because of course we're reusing now the same model. Yeah, before it was just collecting all our variables and constraints, and now as you see in this last cell, it's collecting also the result values, the optimized values. So there are two things. We have this objective value function, which gets the final optimized value from the model, and we have the value function, which can extract the final value for each of the variables as well as for the constraints. So collecting everything into a named tuple, we can see them nicely here. And there comes my first little challenge for you. This also gives some time for questions further. So you see that the optimization was now built such that our v3 became the largest value in this optimization. We wanted to minimize this. And yeah, because of these switches, yeah, a little easy task is to switch this one in the middle, yeah, to make this a 1 kind of, and hence also that the first variable becomes the larger part. So remember what I said, there's this v2 which is binary, which switches between, and yeah, just understanding kind of what is going on gives you also, I think, a good feeling that these constraints, yeah, behave nicely and just that it's doing what it should do, because otherwise it's just numbers so far. But we look into an example in a second. So please just manipulate it a little bit. The numbers you see above, re-execute the cells and see whether you actually got a large variable 1. There's a question. Thank you so much. Yeah. So the v3, as with also the constraints, there's an unnamed variable, which is this v3, and an unnamed constraint, and they can be used normally. They are just kind of a variable, a pointer to this JuMP variable under the hood. And if it's named, then the JuMP variable is also listed inside it by a specific name and hence needs to be unique. And if it's anonymous, it still gets a kind of identifier. It's then referenced by some anonymous name, which is created on the fly. So it exists in the model and it will be optimized, but it's just not accessible like this. And hence, yeah, there are kind of pros for both. Yeah, if you use name style, you can easier refer them in other functions and pass them around. But if you kind of need loops and create stuff in sequence, then of course you need different names and it's tedious to define the names on your own. And then usually you use anonymous variables. We're going to see kind of a third alternative in a second, which is about indexed variables. They are kind of a little in between, but yeah, it's good to know both. So yeah, we see them in a concrete example. So another question, this variable, this anonymous variables, is everything in Julia. They can also be passed to other functions. They would be passed explicitly then, yeah. So usually you always pass the model as the big configuration object, but you can also pass other variables, of course. You can also build your own dictionary which references everything you need. But this is usually not seen in the JuMP code because the model already has this implicit tracking, yeah, of the variables which are named. And the anonymous versions, yeah, depending, often you don't need to reference them because yeah, they're not so needed. But in case you need to reference them, of course, I mean, they're not needed in the sense that they are more intermediate variables, which are like helper variables you need for something to model something, and you don't need to access them directly. But you can, of course, also use this style of variables, and I'm not sure. So what I did sometimes is I wrote a little helper access function, which creates some variables if they don't exist. Yeah, so this kind of style you can also use. You can also create default dictionaries, I can imagine. Yeah, like creating a variable in case you make the access and then use this default dictionary as the big configuration part instead of the model where you bring all the reference together. But in case it works for you, using these named variables and using the model indexing, this is really kind of the preferred way because everyone knows about this. Okay, so I myself haven't tried out, so I want to kind of get this a bit lower. So I'm not sure. So I think the way to go is to make this smaller. Yeah. Okay, this was probably one of the intentions I wanted to give you. Yeah, so if I re-execute this cell, of course it's going to give an error because I'm re-adding a constraint which was already added, a name constraint. So I need to re-execute all the models again. So getting the model in new and then add my changed part objective and re-executing stuff and hoping now it was not successful. I did something wrong. Okay, I think I won't stop here. But this is, of course, a lovely introduction for Pluto. Yeah. So working with JuMP in Jupyter is pretty tedious because of this. And I was thinking about switching to Pluto right away. But in this series, I was using Jupyter. I guess when I redo the series once, I'm going to use Pluto for stuff like this because it's just so much easier if you can, yeah, rerun everything automatically. Okay, so I was not successful. If someone solved it, I'm very happy. But yeah, you could share your constraints in the chat. I'm going on to the first example, which gives it a little more life. So now that we know the basic concepts, it's really kind of straightforward. We have variables, constraints, and an objective, and then we can solve it. And this is kind of the whole thing, which you always do. We can do some simple stuff like having this n queens example, which I took from JuMP. And JuMP documentation actually took it from Matthew Helm and Matthew Tanow. So thank you very much for this very introductory example. And I'm now using model queens as the big config object. And now there's an introduction to this indexed variables. And this is super handy actually if you have a predefined array-like shape of your variables. It's still kind of not, it's very flexible. You can do quite a lot, but sometimes you just need a for loop. Yeah. But many things can be compressed into this index syntax. And as you see here, we have a range and a second range from 1 to n. And this will be interpreted by JuMP to really create this matrix. And because they are standard ranges, we actually got a matrix back. You can actually use whatever kind of index you want. And then JuMP will have their own special matrix-like thing, which you can actually use for many things. And we're going to see it in the second example. Sorry, in the disjunctive programming tutorial. So you can use whatever you want. This is really handy and simplifies working with JuMP. So here I have a little loop. I'm adding constraints inside the loop, so they're usually unnamed. And this is the n queens example. So remember this little image. It's really self-explanatory kind of. We want to place the queens such that they are not seeing each other's. And according to chess rules, queen sees each other's if it's either on the column, on a row, or on the diagonal. And so all these queens, they cannot see each other's. And we kind of first checking the constraints, rows and columns, and then the diagonal. And the way we model this is that all the different positions are binary. So we have this chess field, and we just have a binary value where we want to have a queen. So it's really super straightforward. And this is a typical approach which you take in this integer style optimization or binary optimization in this. And what we can do is just that we restrict the sum. So we're really using the Julia standard sum function here, and we're inputting the whole. Now I must think about it. Is this the column vector? Anyway, we can check this. And of course, so this is the column vector indeed. And this is then the row vector. And we restrict it by this constraint to be exactly 1. So this translates then actually to 2 constraints, one smaller equal and the other larger equal 1, which in total gives you equal 1. And running this, we get this. And the diagonal is now a little bit more mathematical, but this is why I think Julia is really spreading its reach inside this optimization, because we can use now Julia syntax to actually express all these constraints, which is quite handy in such cases where we use the diagonal function and then sum over this. And we use the reverse function to have the other diagonal. So the tilde diagonal, if you want, not sure, 90 degrees tilted. And this is pretty straightforward. And here actually the constraint's a bit weaker. It's smaller equal 1. I'm asking myself why. I think because it just is implicit by the other constraints that, no, they're actually really diagonals which don't have queens. So it's only, there are more diagonals than rows or columns. Makes probably sense. Was not so intuitive for me right now. Okay, so given these constraints, need to execute this. We can solve this, but one further thing, because in real world examples, you usually have also some data, and this is the way you add data to your system. It's the fix function, and it takes a variable and a value, and then will fix the variable to it, this value. And with these fixed values, we can call the optimize function again and get the values from our variable and see that our positions have actually been fixed because Julia starts with 1. This makes sense. So this is first row, second. This is the 5th row and the third column. So it was optimized, and because it found a solution, so everything is nice, and now queen faces each other. You see here a little extra set attribute call, and this is the way to hide the highest optimized output. And here you also see kind of a little bit how JuMP is structured. So there's not a generic hide the output thing, but it's really kind of an attribute of the model, which might be different for another solver. So this is the generic interface, which sets kind of the attributes for your specific solver. Because they are so different, they all have different attributes. This is hard to generalize. But for highs, it's the output flag. And I think they did actually some effort to generalize some parameters, but because they are also different, it's hard. Okay, so a little challenge. Change the initial fixed queens. And special question, what happens if you introduce an infeasible situation? So yeah, let me try this. So again, we need to re-initialize our model and rerun everything. I think we wouldn't have to, but yeah, it's all fine. So now let's put the second queen also on the first row. And now we run into our assertion error, which is super important because this might happen just anywhere. So you always need to check on this, whether your model actually solved. So because we hide our output, we have no output here. But if we set this to true, we also see that the model outputted that it's infeasible. So it actually knew that it can't find a solution. And yeah, this is just important. Sometimes also your time is not enough to find a solution. You will also see this in here. So there are different reasons why a model might not find an output. But yeah, infeasibility is one of them, which can be referred from the constraints. Okay, cool. I take a look back to the chat. No further questions. So the second and last introduction example for this JuMP only introduction is the Sudoku, which has actually two implementations. And if you look into the JuMP documentation, but I'm just adding the second implementation here because it really is kind of a nice addition to what we saw before. So we've been seeing kind of the single variables. We've seen the indexed variables. We're going to use them again, indexed binary variables, which is very, very common. And this now introduces in an indexed integer variable, which is restricted from 1 to 9, namely the numbers which we use in Sudoku. And it's really lovely to see that you don't need to model everything with just binary variables, but you can be more expressive actually. And yeah, so nice. We have again a matrix, this time 9 by 9. And all these can be integer variables. So now the constraints look a little bit different, but this is, you will see this quite a lot in JuMP code. And this is not only applicable to this integer modeling, but also to other parts. And what we use here is a kind of constraint set. A bit too far. So there's from the math opt interface, which is exported by JuMP as an abbreviation for math opt interface, the MOI. And there's an all different constraint set. And you really write it like this, that you have your variable, or in this case, your variable vector, and then an in, or the set symbol equivalent, and then your constraint set. This will be interpreted correctly by JuMP, and some solvers can support this directly, so that they can use this straight away. Yeah, they know, okay, this needs to be all different. I know what to do with this. And for some other solvers which don't support this, there are so-called bridges. This will then be translated to simpler constraints, so that you get the best of both worlds. Yeah, optimizes solvers which have a special support for this. They can use the perfect version, and if they don't support it, you can still use the syntax, and it will just be translated to things which are supported. And another new thing here is that this introduces indexed constraints. So like we had indexed variables, we can also do the same with indexed constraints. I added some spaces, but I think more often it's actually seen without spaces. And yeah, you again use your range, whatever range you want, and you put the variable name and the equal sign in front of it, so that JuMP knows about it and you can use this now as a variable name. So it's a very concise for loop like syntax, and you can also combine this named with names. So Sudoku constraint. So you would just write the name in front of the brackets, and then this is referenced in your model again. You can check this later, then easier. You can use it also without names, which is nice. And this way we can spare some for loops, and yeah, and have for every column and for every row that we specify that all this total row needs to be all different, which translates then to every number being exactly 1 in this row, because we just allow it to be from 1 to 9. So there's left to solve these little sub blocks, and yeah, and using Julia we can write this very concise in a little for loop by using broadcasting, so that we take all the initial positions of our 3x3 blocks and yeah, and use broadcasting to add all the other indexes. And here you get the feeling like it's really connected to the Julia language. Despite being kind of a sub language inside Julia, you really can use Julia style things. Okay, and again, we want to have them all different. So this is a really nice, concise representation of Sudoku, and we can solve this right away. And yeah, as also with the Queen's example, you may have noticed that there was no objective. So it's just specifying the constraints and solving it to find a solution. And similarly here, we're just interested in a solution. So it's a typical thing in these kind of games. Okay, so this took a little while, but now we have a Sudoku, which is of course useless, isn't it? Like we have now one Sudoku here. What you rather like to do is to solve a given Sudoku, or a bit more challenging even to look for a challenge, to look for a Sudoku puzzle which can be solved, which is feasible, but has kind of things missing. And I made this little exercise here. If you like to take the challenge, it would be awesome. Maybe we should do this. Let me take the time. There's this picture which is a bit too large for this screen, but yeah. So if we can take these numbers and try to bring them into the Sudoku as fixed values, and then the algorithm will fix this Sudoku with the fixed values instead of just generating an arbitrary solved Sudoku, which is a bit boring to admit. But the time is going on. I fear I would want to go to the next one. But kind of to give an outline how you would do it. I use the fixed function. So the question is kind of what is the most efficient way to generate this these numbers. I think a second string is a good first thing. And then you kind of may use Julia's awesome concatenation syntax with, so this is kind of taken also from the tutorial on JuMP, with kind of another value to represent the missing. 0 makes sense here. And yeah, and of course I can't remember the numbers. I'm just pretending that I can. And you can even make an extra space if you like, and build your Sudoku just as a matrix. Then you go through it and you fix all your values like you specified it, and then you should be able to solve your Sudoku. Rocco, do you have a question? I guess not, but thank you very much for joining. I'm going to mute you, but please feel welcome to unmute yourself again in case you have a question. So I hope this little JuMP introduction was really concise for you, that you've seen kind of what things you typically use if you build some some optimization problems. It's the sublanguage in Julia. You have these variables and these constraints, and as a third part also the objective, what you want to optimize, and then you just solve it and hope for that it works. So many things can be kind of quite complex. These are, I think, almost everything is NP hard in this realm. So if you scale it, things become difficult, and this is also why there are so many proprietary solvers, which are then really optimized to get all the heuristics in there, so that your super complex problem still can be solved. And yeah, and there's of course a lot more to it in the terms of which kind of constraints you can use. We've just used some simple linear operators, some simple multiplication and addition, but you can also use other parts, and you have also seen now these special constraint sets where there are also a couple of cones which are used in similar manners, which are then which have complex properties, for example, which is kind of also really good to know. There's, if you have this matrix, and in statistical terms, you often want to have a matrix for a variance, which needs to be semi-definite positive, just technical term, which I think is kind of similar, that it's a product out of two vectors. And you can make this a constraint so that you have a matrix which is just exactly like this, which is our semi-definite positive. And you can, by this, express a couple of things. And yeah, so, and if you go to the nonlinear solvers, you can also really take almost arbitrary nonlinear functions. But again, you need to be cautious whether your problem is then solvable. Give it a try, and in which time. And so if this can be kind of tricky to optimize the performance part, because under the hood it's still kind of a black box. You just put it into a solver, and the solver does its work. Okay, great. Then I'd go to the second notebook. So just click this link, or go back to the repository and click the second link. And the new notebook should open itself within under a minute, usually. And mine is already there, so switching the shared tab. Okay, so this is titled Tips and Tricks and Disjunctive Programming. And I find this very helpful to get started with these kind of things, and wanted to share it in here. So this is very important. If you go to the JuMP documentation, you'll see kind of many things. And there's kind of these three subpages, which are particularly important to you if you start using JuMP. Because on the one hand, it looks very much like standard Julia, which you can use, but then still it's kind of this model language inside Julia. So there are restrictions, and such tips and tricks sections as they are these three, and the different optimization parts of JuMP, they are super handy to translate kind of your intuitions, what you would like to build, to what you can actually build inside JuMP. So opening the first link, this is actually the most the richest, where you really have kind of many different things mentioned, which you would like to translate to JuMP: absolute value, L1 norm, infinity norm, max, min, modulo, etc. And this is now the tips and tricks if you look into kind of the left side menu of linear programs. And same for nonlinear and conic programs. I gave the link to you. They have the tips and tricks section, which you might overlook in the beginning, but this is kind of I think, very important to the beginning to kind of see where your intuition might not actually be valid for JuMP programs, and for conic programs similarly. So I think this is kind of the most important part of the documentation, that you get a better understanding where are the limits. And one limit I wanted to replicate here in the notebook, which is the max and min version. And yeah, so I copied it from the page which I just showed you. Again, we create a JuMP model, and we now add 3 variables, namely two variables where we would like to get the maximum of, and another variable, because in JuMP we can only take the maximum as part of optimization. So we have these 3 variables, and we can constrain our top variable to be higher equal than both variables. And then we have this objective as our third primitive, and we just minimize t. And given this, everyone can easily understand that this now approximates the maximum of both. And running this, we should see this. Ah, yeah, okay, forgot to execute the first cell. Typical Jupyter thing. And yeah, so we're back. You can now change this yourself, a little tiny motivator to actually experiment with this notebook. And you see it's really doing the stuff. Yeah, it's really optimizing the maximum of the two. So the key thing is now that this translation of the maximum to our constraint, in this term actually linear program, as you've seen, this is tips and tricks from the linear programming session. You can only apply this to go to the maximum of 2 functions. And you could not do this kind of to minimize onto the minimum of 2 functions. So this wouldn't be possible. You can approach the minimum from the other side, yeah, to have the maximum and approach the minimum really from below. But depending on your setting, this might just not be the option. Yeah, you have kind of some other thing to minimize, and minimization is really crucial, and you need to kind of get this all into one. And yeah, and you don't want to have this value in this minimization or something. So it gets difficult. And in case you're kind of facing this situation, it's good to know that for the nonlinear programs, the JuMP documentation actually has a part about nested optimizations. So in case, this is not linear program, but a nonlinear program, but still there are solvers for this. If you really need to have a maximum inside something as more kind of variable, so like you would like to use it as a function, there's still kind of a way out, namely with a nested optimization, so that you have a minimization problem inside another maximization problem, or the like. So that's good to know. And and this I made a little challenge here before going to the disjunctive programming to look at the page I just showed you for linear programs. Take another example and just bring it here to the Jupyter and execute it. I'm going to do this now. So going to the tips and tricks and silent mode. And choosing something. I think this is nice. So I'm choosing the actually the absolute value, which is really the first. Also a bit lazy here. But it's quite nice because it has a list of several different ways to model it. And I'm going to rename it also to have the absolute name and the model name. That's quite good to see. So this is just the model specification. We still want to solve this. So I think t is the absolute value of x. So let's fix x to something negative. And I copied now the solving part from above. Need to change the model name. And t is actually also the value which we want to look at. Now optimizer. Okay. Nice, correct. So this example is interesting to see because there are a couple of these special constraint sets, which are a little bit like, which you use more like a function actually, but written in this set form. You see here that we have kind of two variables, and we construct a column vector by concatenating these two variables. And then we say that this combination should be more in the math optimization interface norm1 cone. And there are many more of these, but let's take a look at the documentation of the norm1 cone. Okay, not everything is rendered nicely here on my system. I hope the output is a bit nicer for you. Yeah. Okay, this is hard to read, I must admit. It has this example as well, but it tells you like, okay, these the dimensions and the input variables, they need to follow exactly this and this part, and they are concatenated in this or that way. And given that you do everything right, then you get kind of that the t will be the absolute value of the x. And in this part, it's the norm1 cone. So we could have several x's here, and the t would be the norm1 of this. And with one simple value, it's just the absolute value. Okay. So JuMP has a couple of these things, and as said, they often translate also for solvers which don't support this directly. So they are these bridges which help you to use this in a generic way. Okay. Then I'd go to the last part of today with the disjunctive programming. And the motivation you already see here, but checking. You're always invited to ask some further questions. I probably cannot answer everything, but we can also open discussions in case. But I've worked a little here and there with JuMP, so it might be that a couple of things I can answer myself. Okay, so going on. Disjunctive programming. So this was a little personal understanding of disjunctive programming, I have to admit. I am currently in a discussion on one issue on disjunctive programming to actually get my understanding also synchronized with what disjunctive programming is supposed to be. I try to kind of get both worlds together. So I actually, as said in this little introduction here, I got to know disjunctive programming as a nice way to work with a couple of these tips and tricks, and namely the way to work with Boolean operators, which you then model on this binary variables, with disjunctions, which are kind of models like you have one set of constraints or another set of constraints given some binary variable which represents this choice. Or you have indicator constraints, which are really just kind of in case a binary variable is 1, then this constraint should be taken. But however, these indicator constraints, they are custom kind of to a couple of solvers. Not every solver can solve them. The disjunctions are a bit similar to indicator constraints, and quite specific, and has some implementation details which you think, okay, this could be abstracted away. And Boolean operators is the same as like we saw with the absolute value. There are kind of some helpers which you can use to model this. And it turns out that disjunctive programming, the disjunctive programming package, has actually quite nice syntax to model all these three. And yeah, to get back the first example, which we've seen like in a very simplified way, we had a couple of variables where one was binary, and yeah, we have kind of these two choices. Either we have kind of this constraint where our variable is now greater than 4, or we have this constraint where our variable is greater than 6. And as you see, kind of this kind of style, this works only if you have a kind of upper or lower bound. Yeah, so because our variables are greater than 0, yeah, we can build this. If we have another upper or lower bound, we can do kind of similar things, but it comes down to this. And in this way here, it's just kind of very nice to read because the lower bound is 0, so we don't have to name it. But in more complex situations, this actually gets a bit difficult, or at least tedious, and disjunctive programming can do this for us. And as with JuMP, I'd go to kind of the basics, building upon very similar syntax. And the first thing which is actually different is that we don't use the standard model constructor for our big config objects, but we use the GDP model, which has further storage slots for all the extra constraints, which are not part of this normal JuMP model, but will be translated to normal JuMP constraints. I named it model OR because the disjunctive part is usually kind of used for these OR semantics. Okay, so first thing is that we actually get a fourth variable type, which is specifically coming from this package and from disjunctive programming, which is the logical type. And this is really kind of the same as a binary in a sense. It translates directly to the binary variable, but it has special support from this package, and hence the other variable type, so that it doesn't it's not getting confused with the standard binary modeling. So here you need to be really specific. If you use the support for disjunctive programming, then you build logical variables. And here they are named again with index notation, having just these two logical variables. We also get some little extras to work with logical variables, and the most often you use this constraint. Actually, you can even simplify it. I'm going to show this in a second, but it's good to see this. So this is how it works, like a little bit behind the scene. So you can constrain again this vector, taking both variables to be in an exactly one logical constraint, so that really one of these Boolean variables needs to be true. And as you can imagine now, you can have kind of 5 logical variables in this set, which represents all your options. And you say, I want to have 2 of these options to be true. Yeah. Depending on your case, this may make sense or not. And most often it's just exactly 1. And given this, you have kind of laid out how these options interact with one another. In the simplest case, that just one of them should be active. And then what's missing is to define actually the constraints. And we define them here. So we have some further variables, which now just represent some kind of times. And for the super simple example, I'm just restricting kind of that these two events, they should be kind of in order, that either the one or the other is kind of ahead of another. So here it's just a simple +1 and an equal constraint. So solving this, actually it's interesting. Solving this, there should be monotonic increasing, the one or the other, but the order is indeterminate. Okay, this is wrong. Indeterminate. This is the right pronunciation. We are minimizing the sum to get it to 0, and then there's kind of a last part which is really important. So we had kind of these 2 things so far. We have the logical variables, 3 things, which we can actually constrain in special ways using logical constraints. And then we have kind of the constraints which are activated only in case the special logical variable is active, which is put here by this little tag. So this disjunct tag just marks this constraint to be used inside this. But it's actually not added right away to our JuMP model, but we need another disjunction call, which will add this. And we need to call this disjunction on all these variables, which are actually used as this tagging. And yeah, it looks very similar to a standard constraint. And you see here now a special keyword, exactly one equals false. Namely, by default, this disjunction will already add our constraint here. So we can actually hide this and hide this, and it will be the same. It will just be added for us because this is the typical standard case. In disjunctions, it's normally an exactly one. But yeah, the most important thing is that this call will kind of add all the tagged constraints. So this is very important so that the solver does what you want. Because if you don't do this, then these constraints will just be missing. And you see kind of a solution which doesn't match what you want. So always keep in mind that disjunction extra macro is important when using this model. So now let's execute it and see that it does something. So I now I commented this extra constraint, exactly one, this through it. And then, yeah, this is the way I solve this lower bound issue. Again, with fixing, I'm fixing x1. And because we want to minimize it, the other x2 should be lower than it. Yeah, so we would expect 3 and 2 as the solution. We optimize it and let's hope for the best. Yeah, it's working. And to see that it actually is really working, you can fix another variable to the other one. But as before, unfortunately, in Jupyter, it's always important to re-execute everything. And now we see kind of the same, just the reverse. We fixed the second variable, and the other one is below it. And it just happens that a couple of times you need these order relationships in your constraints. And one example which I wanted to share here with the public is the just scheduling example, that you have a couple of tasks and a couple of workers, and you would like to match them so that the worker is running all the tasks. And this is just a nice little thing which you can do with disjunctive programming. And yeah, so and it also shows you as a last and final example the real use of the arbitrary indexes. But first, kind of, I want to check whether there are some further questions. Okay, there aren't. So then I jump to the last example, the last introductory example for today. I define a couple of tasks and workers. And as you see, I'm converting them to symbols. I was opening a little issue here to track this. It turns out this is already solved on the main branch. It's just not released yet. It's a little thing from the macro that it has something that doesn't work with strings, but it works with symbols. And good for now, we just use symbols, all fine. And yeah, so we have a couple of tasks for our imagined bicycle shop. And we want to repair bicycle 1, bicycle 2. We have some orders. And I think that's wrong. Huh? Anyway, we have some other tasks that we need to be at the service desk, do stuff, do some calling, and of course, very important to have an odd number of tasks, just relax. Because bicycle stores also need to be careful about getting their workers. There are a lot of programmers out there, but there are not so many who like to kind of fix bikes. We have a couple of workers, And to be more explicitly inclusive, I chose some names which are also not that common for me, but I think it's important to bring them yeah, as more standard and common into today's world. And I'm now creating our model bicycle as our GDP model wrapper, which we can optimize if you've seen just like a normal JuMP model. It's really just with starting with another wrapper. Okay, so what I'm doing first is I'm going to create a couple of time variables for my tasks. Namely, every task should be scheduled on a time. This is nice. You can see this. Like we again using just our index brackets, but instead of using 1 to n, we are just using our vector of tasks. This will construct our times variable, which we can actually take a look. Model times. So there it is. But it's on model. There it is. And we can also, of course, because it's macro itself, we also have it at the variable times. And you see that it's nicely indexed. And this is now called a dense access array, which is kind of JuMP's special support for exactly these kind of things. And yeah, that's nice. So it works a bit like a dictionary, but has this order. And makes it for us very intuitive to work with it. The next part is now a bit more complex, but I wanted to show you kind of this style of working that you can do even this thing with disjunctive programming. So what I'm going to initialize here is a complex matrix of logical variables, which I named assign to have this kind of that one task is assigned to one worker. So we're going to restrict this and constrain this in the next line. Namely, we want to restrict it that for every task we have this index notation. We want that it's really assigned only to one work. So here you can actually imagine, yeah, here it comes in handy. Yeah, so we have a couple of workers, and we may have a couple of tasks which should be assigned to 2 workers. Yeah, so this is super easy now to change this. Yeah, we just would have a 2. Of course, with 2 workers in total, it doesn't make too much sense here, but you get the idea. Yeah, so we have our constraint modeled explicitly that every task should be assigned to 1 worker in this case. And now we need to get a little in the detail, because if you now imagine, okay, what does it mean? Now, what do we want to constrain? We want to constrain the times, actually also in a second manner, namely that each worker, of course, or no, not of course, in this little scenario, each worker should only do one task at one time. I think this is in general a good thing to do. Yeah. So this multitasking, I guess some studies show that it's in most cases not working really well, but people are better when concentrating on a single task at the time. So we want to model this here as well, so that each worker is just doing one thing at one time. So this means that we need to somehow need to make sure that all the tasks for one worker are not overlapping. And it turns out this is a little more difficult, but I think it's nice to get an understanding that this is quite flexible. And the thing is that if you think about it, so okay, now I want to say that all for worker 1, all the tasks should be one after another. Super simple. I still face the difficulty that I don't know which task actually is for worker 1. And it's even kind of in this way that I have almost no way to get this list explicitly, because it would mean kind of to first distribute the tasks to the worker and then optimize for the times when these come. But usually you want to optimize this in one go, that you optimize the times when which task needs to be done at the same time as you want to optimize kind of which task is put to which worker, so that you really kind of are efficient at solving the tasks. So you, in this scenario, you don't know which task is assigned to a worker, but you really need to do it in a flexible manner. And as it turns out, please correct me if I'm wrong, which is one of the reasons why I'm putting this here. So there might be a better way to represent this. I really welcome every suggestion or hint how to do it. But the best way I found so far is to look at the pairs, to really kind of get a quadratic complexity in it here, yeah, which is a bit disadvantage. It's a little disadvantage, but I haven't found a better way. So because I'm still not knowing which task is for which workers, I'm looking at all the pairs and make sure that they are not overlapping. So because overlapping is kind of okay if I just do it on pairs, then nothing will overlap. If the pairs don't overlap, this should be kind of nice. And for this small part, yeah, the pairs are still kind of okay to have a look at. And I'm creating a special, an explicit vector to really enumerate all these pairs. And yeah, as you see, kind of as it is usual with pairs, it's not the quadratic complexity. It's a bit lower. I'm going from 1 to the length of the task -1 for the first, and the second I'm going to start at y + 1, and then going to the end. And this way I am really looking at every pair only once. And good to know for you, actually, you could use this kind of dependent index variables also in the JuMP index syntax. But here, I thought it's easier to really kind of create the pairs first, because we're now going to use them in our modeling. And concretely, what I'm doing here is I'm defining a logical variable, which is now, again, an assigned, but now assigned pair. Before we had the assigned tasks. Now we assign a task pair to the workers, but it's the very same idea. And we use now what is actually supported by disjunctive programming, the special logical constraints. So we do some index constraints again for all task pairs and all workers. We define that we actually assign this pair to the worker just exactly if we assign the first of the pair and the second task of the pair to the same worker. And notice that the parentheses are very crucial here. And yeah, as this is a constraint, the syntax actually requires you also to put this last special equal true. But it still looks kind of nice and very concise. And with this, we constrain now our logical value to be dependent on the other assignment, where we had this exactly one constraint on it. And yeah, given this now that we kind of, our logical definition of the assigned pair is now fixed, they are depending on the normal assignment of task to workers. And now having this assigned pair, we can actually define our non-overlapping constraint, which is very, very simple here. It's again this +1, but now with the smaller equal, because we of course don't know where this pair now is. It could be kind of the first and comparing the first and the last. Yeah, could be comparing the first and the second, and hence a smaller equal makes a lot of sense here, so that they are ordered. And this is now our disjunctive constraint. So we tag this with a disjunct and exactly on our assigned pair logical variable. So this is really the style disjunctive programming works. You have your normal constraint, and in addition, you tag it with a situation when this constraint should be active, which is your logical variable. So last part, super important. This won't work without it. You can give it a try. We need to inform disjunctive modeling, disjunctive programming, sorry, to actually rephrase these tagged constraints to actual JuMP constraints. And yeah, here the disjunction macro is super important. And because we now modeled our logical variables independent of this standard exactly one, we had a little more complex logical modeling. We add this exactly one equals false. And I was told to tell you kind of that this is a very special use of disjunctive programming. I'm not sure how special this is. I find it very intuitive and easy and straightforward, like a nice extension of the tips and tricks section of standard JuMP. Hence, yeah, tips and tricks and disjunctive programming. Yeah, but I should make a link here also to this issue where I'm currently motivating a discussion about this. So the standard disjunctive programming paradigm is often usually using exactly one constraints. But as you see in this case, it works pretty well without exactly one constraints, and also the package documentation itself describes it. And I hope the documentation will be a bit more explicit in the future about possible pitfalls, what could kind of be not supported if you use if you use exactly one equals false. This just as a little tiny warning, but as I understood the package, this is kind of still totally valid. And as you see, it also fits pretty well to the syntax. So this package is made for being used in this way because it supports all these things. Yeah, just this line looks like a little awkward, which is why I opened an issue. Yeah, having to place this exactly one equals false looks like a bit weird, and hence I wanted to give this further background information to you. Okay, so now we can solve it. And I'm now setting an objective to minimize the times, because otherwise there would be kind of somewhere. And yeah, and we can take a look. These are the times. So just every task is scheduled at one time. And we can already kind of get an idea which task is scheduled to which worker just by looking at this. We had a very simple modeling, which assumes that the tasks are executed in order. Yeah, so this is why you see it really being increasing, like with 2 workers. We can also access the assignment variable, and here we first need to map it to the respective JuMP variable. So this assign was a logical variable, and there's a special access or mapping function called binary variable, which maps this to the actual JuMP variable, which is binary, and there we can extract the values. So this little extra step is needed for this logical variables. And here we see that they are nicely kind of really spread out to the workers, which makes sense if we want to minimize the overall time. Yeah, so the best approach is to spread out the work equally. And I think this is a really nice little thing where you see how you can kind of model complex logical things into JuMP, which otherwise might be super tricky. And I like this, that the disjunctive programming gives you this access. And because of this overlap with the tips and tricks section, I think it also fits quite well to an introductory session about JuMP. So I put the both together, put the two together. So this is the last challenge here. Add further tasks, further workers, and see that it also scales there. But of course, be careful. Yeah, you see there's this quadratic dependency on the number of tasks. And yeah, and as usual, these things are hard to optimize in general. So you need to be careful in scaling. And yeah, but still it's cool to see that with kind of a couple of concepts, you are already able to use JuMP for these kind of things. Okay, then I'm going to do this last little tiny look on the time. Yeah, we are approaching 8 o'clock as usual. So I have a couple of minutes to actually do further tasks and further workers. And I'm probably super uncreative. What kind of task can you do for bicycle job? Uh, um, the wheel. I'm not sure whether this is kind of fluent English. This special English, yeah, I've always have problems. Um, this is always good. Um, yeah, should be enough. And I need to re-initialize the model. Yeah, it comes below actually. Yeah, so workers. We have a couple of more workers. We want to spread it out. An English name, German name. Okay. The Spanish name? Not sure. What's this? Paulo. 5 workers. So reinitializing the model and creating our assignment matrix, restricting that we only want 1 worker assigned. Actually, this is cool. Let's take a look and assign 2 workers. We need to rerun the model. And again, because this approach, models the non-overlapping part by just modeling that the pairs don't overlap. We have the pairs. 45, it's still kind of really reasonable. And now adding such constraints, making sure that the disjunctive constraints are actually rewritten into normal JuMP constraints, and setting the objective and solving it. So that's nice. I also changed this exactly 1 to exactly 2. So let's see. I haven't tried this before. So in worst case, something fails miserably because it's live, but let's hope for the best. Because it's not too much larger, and in the first time we also have probably had some compilation part. I hope that this is going to come back to us within the next seconds. But it could, of course, also be that this exactly 2 constraint is now making the model so much more complex that solving it is actually quite tough. So a little side note here, because it's still optimizing, I want to give it some more seconds. When introducing the times variable, I made sure that actually the times not only have a lower bound, which makes a lot of sense for times, but also have an upper bound. So just from experience, this enables the solver to solve things so much more quickly. And usually it's super reasonable for whatever concrete task you have, that you can set an upper bound actually. Okay, so it looks like this is not quickly coming back, which I think is also a good demonstration. Yeah, so while you can model a lot of things with JuMP, because of this NP hard, of this being NP hard under the hood, you always need to be cautious that it might scale miserably. And it might also, it's probably, so Heis is not the best optimizer out there. So changing it to some other proprietary solver would, could probably speed it up. This is an option. Or you just have to get a feeling of how this complexity scales. So I'm afraid it won't show its result to us. I would need to change to exactly 1 constraint, because it can't imagine that adding a couple of tasks now is doing it already. Okay, I'm interrupting it. I was fearing it like this, because the Heis optimizer is actually also an external dependency. This couldn't be stopped safely within Julia itself. But killed the Julia kernel. It's okay. And so relaxing this exactly 2 constraint. And need to port it. Okay, so it might still not work now on the run, but I hope where Where am I? There I am. Okay. Exactly one constraint now. Task pairs. And solving it with some compilation time up front. Okay, so I hope you got a good overview about how you can deal with JuMP. I think it's pretty intuitive once you see these examples. Yeah, you sometimes have to translate your usual functional style of applying a function to something. This works super similar for linear functions and similar parts which are expressible within your JuMP solver. But as soon as you get a bit more complex, you or nonlinear, you need to think about how to you represent it inside JuMP. And then are of course also these optimization parts related to NP hard. So you can lose quite some nerves about how complex your solution space actually is currently, and whether adding some further constraints here or there may actually simplify your space significantly so that the solver finds some solution in a quicker time. And I think here, for example, so we have introduced an order among the times, but a simple simplification to the model would probably be to add some further constraints on the workers so that they have a natural ordering. Just taking the standard ordering of the workers. So I guess this would, this would solve it quite some time, because actually, so this would be kind of a good final note to make here, but now you just hear it from me. So this is actually trying to find the optimal solution. And it's going to be for another session, I have to fear, because I'm not sure about finding the right terms now. But in this example, you're just interested in a feasible solution. Yeah, this would be already totally fine. And so you want to interact with the solver. Heis has also kind of some parameter for it, so that you could early stop the optimization problem to just return the first feasible solution, which fulfills all your constraints. I'm not looking for an optimal solution. I guess this is kind of one of the key things why this is taking more time, and hence adding some further constraints on even the order of the workers can speed up things drastically, because it doesn't need to take a look at so many options and has more pre-knowledge about where the optimal solution lies. Okay, so we won't see the solution here today. I fear it's probably in the range of minutes, because the model is still constructed the way it is. It's the way it is. It's 8 o'clock. I'm there for further questions, but I think it's a good time to stop here. And thank you all for participating. I'm glad I could give another introduction on JuMP. I hope you learned something today and feel a bit more confident with starting using JuMP. It has some black magic holes, but I hope I could give you the right pointers that you feel more confident now to actually try it out and have a better understanding, where the difficulties or the complexity lies. Still computing. And unfortunately, interrupting it will not give us access to the feasible solutions. Oh, it's there. It's there. Nice. Okay, we had enough workers. So we see that every worker just has 2 jobs, which leaves us with a 0 and 1 times. And yeah, okay, so at least this worked. We could scale it, and we already got some experience that yeah, it really takes more time to solve kind of a more complex problem. Thanks for being there, and thanks also for watching the recording if you're watching the recording. See you soon, latest on JuliaCon this year, I guess.